In this lecture, we will be covering the topic of regression model selection, specifically working with multilinear regressions. And so when we are selecting a model, we are really balancing two different principles. So the first principle would be larger models. We tend to favor larger models with more predictor variables. The idea here is the more predictor variables you have, the more information you are using, you're mining in this linear regression sense to predict the response variable. And because of that, you have less bias. But the problem is, for every additional predictor that you have another coefficient that you have to estimate. And with the estimation of coefficients comes error. And having more and more coefficients introduces more and more error. And so having a lot of coefficients is not necessarily better. And that leads us to a preference for smaller models, smaller meaning fewer predictor variables, because of this issue with error in the estimation of the coefficients. When unknown coefficients are replaced by estimators, we lose accuracy. And so more coefficients gives us more severe of an effect of that. And so we prefer smaller models when possible to not have as much of that type of error. And so we have a balance here. So some people may naively say, just use every predictor variable that you can think of. Throw the kitchen sink at the problem. But it's this issue of error in the estimation of the coefficients that generally makes that not a good idea. So you want to find that point where you're properly balancing between these two ideas. In statistics, we often call this the concept of parsimony. So let's think about the selection criteria that we might use for our predictors. So let's write down our standard multilinear regression model. So we have our ith response here is equal to this linear combination of the ith case for predictors, x1 up through xm, and each one of these predictors has its own beta coefficient, and then we add a white noise term, epsilon I, where these white noise are all IID, mean zero, variance sigma epsilon squared. And so we have n observations. Each observation has one observation of the predictor vector x and the response y. Little n observations. And the idea here is that x has, we will say, m elements. So we'll have m predictors. In our previous regression lectures, we had p predictors, but we're switching to m here for a reason. When we develop this CP, it will be handy. So let's talk about AIC, BIC, R squared and adjusted R squared, and CP as our criteria for deciding how many of our predictor variables we should use. The first criteria we look at is Akaike's information criteria, usually just called AIC. And that is defined in this way, although this is really a standard approximation we use to it. But we have n times the log of the estimate that we get for the variance of the white noise, sigma epsilon squared hat, plus 2 times m plus 1. And really, our choice here boils down to m. So m, remember, is a number of predictors. And we want to minimize this AIC criteria. So think of n as fixed. We prefer to have a smaller sigma epsilon squared. Think about if that's going to 0 and we're taking the natural log of it, we know that the natural log of x looks like this. And so if we're plugging in small values for x, we're getting something largely negative. So the smaller and smaller, closer to 0 this sigma epsilon squared hat gets, the more negative this natural log term is getting. So this is a term that we want to push down. We want to minimize that, and that is a goodness of fit term because it's making the observed data more and more likely, as represented by a smaller variance of the white noise term, namely this term in the regression. So this is a term we want to minimize. Minimizing that helps us with a better fit for our model. At the same time, we prefer a smaller number of parameters. M plus 1 is the number of the beta coefficients that we have. Recall we have M predictors. Each one gets a beta, but then you have your intercept beta naught. And so we want to push this term down. And this builds that trade-off into trying to minimize the AIC overall. A larger M will help this term get smaller, but it will increase this term. Conversely, a smaller M increases this term, but decreases this term. So we are balancing that goodness of fit versus smaller number of parameters here by balancing these two terms. The BIC, or the Bayesian information criteria, is very similar. The difference is, instead of a 2, we have a natural log n. So the principle is the same. This is a goodness of fit term, which we are trying to minimize. And this is a penalty on the number of parameters, which we're also trying to minimize. And minimizing both causes a trade-off between goodness of fit and use of few parameters. And we can compare these two and see that the only difference, again, is that 2 in the parameter penalty term for the AIC versus the natural log n in the penalty term for the parameters in the BIC. And we note that natural log n exceeds 2 once you get past 8. So typically with these types of models, we have more than 8 observations. And so the idea is that the BIC is penalizing your number of parameters more severely than the AIC. And so your AIC will usually choose more parameters than the BIC. So this gives us one standard set of criteria for choosing the number of predictors. We have also seen in our studies of regression the idea of R squared. R squared is the regression sum of squares divided by the total sum of squares. And so recall that the idea here is in the denominator, you have the total variation in the response y, in the response variable. And in the top, you have the total variation in the response y that can actually be predicted by x. And so on a percentage basis, this tells you the percentage of variation in the response y that can be predicted by x in the linear sense, because we're doing a linear regression. And so this is going to be something between 0 and 1, and the larger the better. So the closer this is to 1, the more explanatory power we have in our regression model. We also can use the adjusted R squared if we care about adjusting for bias. And we refer to the lecture on regression and specifically analysis of variance part 1 and 2 to understand more about using R squared and adjusted R squared in this way. Another concept is this one of Mallow's CP. And the idea here is that we're going to estimate how well a model predicts responses with new predictors. And we're going to try to address overfitting here through use of CP. And really the idea here is that you have a set of M predictors, and you want to try to decide how many of them, more specifically, what subset of them you should use. And we do that by using this residual error sum of squares, SSE. So let's recall that the residual error sum of squares is defined in this way. So it's the sum over all the observations of the squared difference between the observed response and the fitted response. The fitted response coming from your regression. And so this, when you add it all up, represents the variation in y that cannot be predicted by the linear regression onto x. This is actually, if you look at the case of just one predictor, what you have here, say in the ith case, if you have your regression line, here would be your x sub I, and then here is your point y sub I, and your fitted y sub I is what you get if you use the regression line above that predictor. And this difference here, this vertical difference between the two, is exactly this difference we have here. And so that's how much your regression predicted value is off from the actual observed value. So again, this is that variation in y that cannot be predicted by your regression. And we take this sum of squared errors, the residual sum of squared errors, your SSE, and we multiply this by 1 over n minus p minus 1, and that gives us an estimate of the variance, the sample variance, for the variance of the white noise terms sigma sub epsilon squared. And again, the key thing here is to recognize we're thinking of this using all m of our predictors. And the question then becomes, what happens if we use fewer than m predictors? And that's why we define what we'll call the residual sum of squared error, SSE, of p. So this will be the SSE that we get if we use p, fewer than m, predictors. Now the idea to define Mallow's CP is to take the ratio of that SSEP over that sigma epsilon m squared hat, and then minus n plus 2 times p plus 1. And when you look at this, you want to think of getting a CP as a result of a choice of a subset of the m predictors of size p. And so the less variation that can't be explained by the regression, the better. So this numerator is varying with your choice of your subset of predictors. The denominator is not. And so the idea is you want to have a lower numerator here. So this is a goodness of fit term. The better your regression, as measured by the SSE with your p predictors, the smaller this term. So this term we want to go down. Then we have n, which is not varying. That's our sample size. And then we have 2 times p plus 1. This is a penalty on the number of parameters. And so this is another term that we want to minimize. And so we again have this balance where this term is being minimized for a goodness of fit term, and this term is being minimized to penalize our parameters. And that gives us this parsimonious way of using a term to minimize that balances goodness of fit and trying to err on the side of fewer parameters. And the idea here is for a model with a little bias, CP should be approximately p plus 1. That's its expectation, is p plus 1. And so intuitively, if your CP comes out much larger than p plus 1, this indicates an underfit. And for cases where p is large, if your CP is close to p plus 1, that's typically an indication of overfitting. So this gives us 3 different tools: CP, R squared or adjusted R squared, and our AIC, BIC criteria that can help us select not only the total number of predictors, but given a set of predictors, which one should we use? We'll develop this idea further because we need to address an issue of collinearity, which will come up in a subsequent lecture. But it's important to recognize that what we're really starting to do is look at a regression problem in a bit more of a sophisticated way than just saying we have all these predictor variables, let's just use everything to do a linear regression for the response. We really want to start looking at the data that we have and deciding what we should use as predictors and what we should omit. And these tools help us start to do that in an informed way.